In this video, I want to introduce the generic cyclic group of order n. When we look at theorems about cyclic groups, they are usually written in this particular kind of notation, and that's why I want to look at it. We're going to let G be a group that is generated by the symbol little g, where what we know about little g is that little g raised to the n is equal to the group identity for the group capital G. What I want to notice is that we actually know some things about this particular group. We know that G itself consists of the symbols E, G, G squared, all the way out to G to the n minus 1. And after that, the powers start to wrap. E is equal to G to the n. That G can also be thought of as G to the n plus 1. G squared will be G to the n plus 2, and so on. So one of the things that it is important to realize is that the order of this cyclic group is equal to the order of its generator, and that means the order of this group is equal to n, and we often call G the cyclic group of order n. Now, if you think about it, the English implication of saying that G is the cyclic group of order n implies that there's not more than one of them, and we have to kind of investigate what that means. But before doing that, I want to actually kind of look at how the multiplication works in this particular generic cyclic group. If I have G to the K and G to the L, both belonging to my cyclic group, then the way that I multiply them is just through exponent rules. I'm going to look at this being G to the K plus L. The only thing is I can reduce K plus L modulo n. So I want to say that this product is equal to G to the K plus L, where K plus L is reduced modulo n, where that n is equal to the order of the group, and that means the order of the generator. Let me look at a specific example of how this means. If I let G be the cyclic group where the order of the generator is equal to 5, and that means G to the 5th is equal to E, then if I'm looking at G to the 4th times G to the 4th, that would be G to the 8th under exponent rules, but since G to the 5th is equal to E, we can reduce that exponent mod 5 and treat that G to the 8th exactly like it is a G cubed. And the reason that we can do this is because G to the 8th will be G to the 5th times G cubed, and G to the 5th is just an E, so we're looking at E times G cubed, and E times anything, of course, is the anything. Now, what I want to do next is I want to think about the fact that we're doing modular arithmetic on the exponents means this generic group looks a lot like Zn. So let me write that down. So since in G equal to a generic group where the order of the generator is equal to n, since in this group G to the K times G to the L is just G to the K plus L, where K plus L is reduced mod n, the actual structure of our cyclic group should look like, so it should look like, let me correct my handwriting there. This should look like Zn under its addition in some kind of fashion. And as an example, I want to consider looking at, so I want to look at G equal to the cyclic group where the generator has order 5, and I want to look at Z5 under its plus. And that's going to be my example. And I have this written down on the next page. And what I would encourage you to do is to stop the video and copy down both of these Cayley tables. And after you have them copied down in your notes, start the video so that you can listen to what I am saying about them. So hopefully you've done that. What I want to notice is that everywhere where there is an E over in the Cayley table for the generic cyclic group, there is a 0 over here in Z5. And wherever there is a G, which is a G to the 1, there's a 1 over here. And wherever there is a G2, there's a 2 in this table. And I'm kind of highlighting those guys, and the 2's come here. And then wherever there's a G cubed, there's a 3 in the table for Z5. And finally, wherever there's a G4, there's a 4 over here in the Cayley table for Z4. In other words, the structure of the two tables is the same. The only thing that is different is that over here in the table on the left, we've got additional notation for the G's, and over here we've just got the exponents. That's really all the difference is that the Z5 table, we've got the exponents, because after all, these E's are all G to the zeros, and the G's themselves are all G to the ones. So if we throw the G notation away, the tables become the same. When two groups have a Cayley table that is exactly the same in terms of the structure, but we've changed the names of the elements, the groups are said to be isomorphic, and that's an idea that I want to get written down. So when two groups have the same structure, in their Cayley table, we call the groups isomorphic. We write G is isomorphic to H when G and H are isomorphic groups. Now, I have not formally defined what an isomorphism is. We will do that later in the semester, but right now this informal notion is good enough. And it's important to realize that what I mean by same structure is that the Cayley tables are identical except for the name of the elements. So the Cayley tables are identical except for the names of the elements. So if I go back to look at those Cayley tables for my generic cyclic group of order 5 and Z5, we can see that this G is indeed isomorphic to Z5 because the two tables are exactly the same. Well, it turns out that if I look at the Cayley table for a generic cyclic group of order n, So let me say where g to the n is equal to e, the Cayley table for that generic one, and the Cayley table for Zn under its addition will be exactly the same in structure. So they will have the same structure. It's just that in the Cayley table for the generic cyclic group, we will have GK times GL will be written as GK plus L. And over in the Zn table, we will have K plus L will be written down in whatever the K plus L is, mod n. And it's just that this exponent, because it is reduced mod n, will look exactly the same as the K plus L over in the Cayley table for Zn under plus. So what we have then is that every cyclic group of order n is going to be isomorphic to Zn under its addition. It's just that when we want to write groups multiplicatively, we will write the cyclic group multiplicatively as a generic group of order n, where we know that g to the n is equal to e. So these two groups are going to be isomorphic to each other.